Mhm.
Okay, let me check the spreadsheet. Okay, spreadsheet. Then, okay. I want you also to update the document, but it's fine. You can do that offline. But please do.
With the so the solution, should I put like a link to
Yeah,
GitHub?
yeah. Yes, please.
Oh, okay. Sorry.
Yeah, and don't
I
forget
didn't
the
know.
time complexity and memory complexity
Mhm.
with explanation, of course. So, what we have done,
Mhm.
I mean, we have discussed that together orally in the session, but then you have to figure it out by yourself because you might forget it, you know. I don't know. Sometimes we take notes in the playground, but to make sure that everything is noted, you have to answer them by yourself and explain the thought process. Why is it of n squared or 2 to the n or whatever? And
Mhm.
yeah, I'll be looking at the answers and giving comments if they're in.
Okay.
Okay, so yeah, do you have any questions first?
Yes. About the number two problem that says uh, write a function to find the number of unique paths from the root till the end of the BST.
Mm-hmm.
At first, I wasn't sure how to find a unique path because, since it's recursive, I didn't know if two function calls could end in the same path going to the end, and how would I like put that in a number.
Mm-hmm. Okay, so do you know how a BST looks like?
Yeah. So it's oh no, I maybe I'm thinking of a just a binary tree, but it has to be
Okay, can you share
a
your
node
screen?
can have two children. Yeah. Should I go to a playground?
Hold on. Let's let's share your screen, and then I want you to look at some binary search trees, and then we'll see.
Okay.
Okay.
So wait, can you see it?
Yeah. Okay. So go to visualgo.net. Visualgo. This website.
Sorry?
I'm typing it down. Visualgo.
Visual. Okay.
Yeah. Okay. Look for binary search tree. Yeah, the one on the right, left. Yes. Just escape. No need to read it.
Oh,
Okay.
okay. Yeah. So yeah, all the nodes to the left are smaller than the ones on the right. Okay.
Mhm. Okay, can you answer the question for this example?
What question? Sorry, I'm not hearing you very well.
Oh, I'm sorry. Can you answer the question that is uh, finding the number of unique paths?
Unique. Um, well,
Is my voice better now?
yeah.
Okay.
So using just like a normal recursive call to
Oh
every
no.
node on the left and every node on the right.
We will talk about how the solution works later. But now, can you answer for this example?
Oh,
Can you give me the answer?
okay. Yeah. So I would say 5.
5. Okay. Can you show me the paths?
Yeah. So all the way to the left, here is
Mm-hmm.
1.
Yeah.
Then here is 2,
Yes.
and 3,
Yeah.
and then 4, and
Yeah.
then 5.
Cool. Nice. Okay. Can you create another tree? Go to create, the bottom left. Create balanced example. Yeah. Okay. Now, what's the answer?
So 1, then 2, 3, 4, and 5.
Yes. Exactly. Okay. Can you add? Choose a number that you want to add to the binary search tree.
17.
17. Okay, we don't have 17. Yeah. Go to, insert. Type 17.
Here,
Yeah.
17.
Look what happens.
Like, ooh, yeah, because it's a binary search tree. Okay, yeah.
Hmm. Okay, now can you insert 15? Hold on. 10, 10. Okay, you can use the buttons on the bottom to go left or like to see step by step
Okay. Mhm.
what happens.
So,
Hmm. Yeah, you can go all
okay.
the way to the right now. We want to see the full tree. Okay, what's the answer now?
So 1, and then 2, 3, 4, 5, 6.
Okay, cool. So, what is your approach? What are you doing to find the number of unique paths?
Well, um, I'm seeing like it's like the traversal.
Mhm.
It's it's like a depth first search or breadth first search,
Yeah,
or
that's right.
okay. So this is depth first search because we're
Yes.
going all the way to the root,
And
all
now,
the way to the leaf.
yeah, you always depth first is go deep first because you have a choice to either explore the whole level that's right after you or go deep. So
Hmm.
depth first is go this deep first.
Hmm. Yeah. So and we're searching both children to be no pointers.
Ch- Children, do you know pointers?
The children, because since we're doing the
Mm-hmm.
first search,
Yeah.
well, we would go here and here and here until this node has no pointers both left and right. So that means it's the
A
leaf
leaf.
node, and there's
A leaf node. Yeah. A leaf node. That's right. Yes. Okay. Do you know how to code that?
I don't, but well, I've done it before, but
You do.
should I use this?
You do know.
Yeah, yeah. Okay, wait, sorry. Mira que estoy en clase. My dog wanted to come in really badly.
Oh,
Um, so, okay. Uh, breadth research is go to all the, take a node, go through all of the children of that node before selecting the next. And depth is go to all the children before starting on the next child on the level. Wait, I'm
hold on,
confusing
hold
my.
on, hold on. Do you know prefix order, infix, and postfix order?
Yeah, well, I don't remember, but I have.
Okay, you can look that up.
Okay, it was last semester. Uh, wait, this one was update. No. Mm, mm, no, but okay, no, no, no. Pre-order is um
You can make a Google search.
okay.
See.
So pre-order in order. Okay, so here we're trying to do um, we're trying to do 4, 5, 3. Hmm. So post order because
You can look at the pseudocode. It's there.
so, so traverse the left subtree. Oh,
Now have a look at the code and see how easy it is.
yeah, I remember that it's like 3 lines,
Yeah.
but I don't remember the 3 lines.
Do you remember now? Let's look at in order. By the way, all of them work. Let's look at in order.
Okay, okay. Wait, there's a node, print post order. Yeah. Okay, yeah. Mm-hmm. So, okay. So I would do these two lines, and then if that node has two children that are no pointers, then I would add one to the counter. That's what I'm doing.
Maybe.
Okay. Should I code it up?
Yeah.
Okay.
You have 10 minutes.
Okay. Wait, so this is
And you
going to
should be able
be...
to do it in less than 5. But I'm gonna
Okay.
give you 10.
Wait. So don't start yet, because I need to get this. No, but I'm still gonna, no. Okay, so wait, no. Okay, start the timer. Int.
Can you start it on your
Oh,
machine?
on my phone. Yeah. Wait, what?
Yeah. Not well. I prefer to see it on the web, to be honest.
Oh, okay. Yeah. Wait, let me get...
Stopwatch.
Oh, yeah. Okay, can you see everything?
Yeah.
Okay. Okay. So if root no. Wait, no. So
We're not gonna create a function.
oh, yeah. And do I need to put this? No, I don't. Okay. Wait, I think I'm missing something.
You're not. That's correct. Okay. Now, can you update it and remove the counter and make the function return the result? You have a small problem. Let me show it to you. But it's not a big issue. Look, you have an int, and here you return 0. So you either do void and do this. Now this is correct.
Oh, okay.
But what I need is the thought process, okay? It's fine. So now I want you to remove this, and I want unique paths to return with the result. So when you do, unique paths on a certain new node, whatever, 5, it's gonna give you the result. Okay.
Okay. Okay, so I need an int.
No, without an int. The function itself returns the result.
Oh, okay, okay, okay. Ah, easy, easy. So, so the return has to have the recursive calls, and I need to add. Wait. Mm, mm. Um, okay, so I need to have some sort of sum in the return. I'm trying to think what that might look like. So,
Okay, so if you find yourself confused, you don't know how to write it down. First, you need to know that it's a recursive function. Think of the base case and the recursive relationship. What can you start with? The base case or the recursive relationship?
the base case.
Okay, the base case is easier to start with.
Mm-hmm.
Uh, okay, here, this is a bit big, but okay. What's the result for the root node of 11?
2,
Why 2?
because the right doesn't have any the right node doesn't have any children, and the left node doesn't have any children.
Okay, what's the result of 10?
0.
Why 0?
Oh, because it doesn't have any children, and it is the root.
Is there a path? A unique path?
To 10, no. Or yes, doing nothing. Is that a unique path?
Yes, it is a unique path. It's a path
Oh, okay.
that has one step. So the answer is 1 here, right?
But what step does it have?
It doesn't have to have a step. I just said path. There is a
Oh,
path.
okay, okay. Okay.
From the root to a leaf, and the root is the leaf. So a path, that's a path. Okay, so the answer here
Okay.
is 1. Here,
Also 1.
also 1. Okay, so when it's a
Oh.
leaf, the result is 1.
Mm-hmm.
What can you do with that piece of information?
So,
You have
oh,
to,
because all the leaves represent a different unique path. So,
mhm.
and all of them have one path, so I would just, okay. So I just need to add all the leaves.
Yes, it's like you're counting the leaves.
Mm-hmm. Okay. Um, Okay, so here would be return 1 plus, but then how would I?
Samuel, you are at a leaf. That case is a base case. When you are at
Okay,
the 10, you do 1 plus what? You are at a leaf. What do you have?
mhm, return 1.
Yeah.
Okay, okay.
What else? If you have something else to add, what is it? There's only a leaf. I mean, after you, there's a null pointer on the right and null pointer on the
Mhm.
left. And
Okay.
also you have to stop because that's the path.
Yeah. What I was thinking is to like have the I don't remember which one. Oh yeah, the max sum, where we did like the tree to
Mm-hmm.
the left plus the value
Mm-hmm.
of the node plus the tree to the right. But yeah, since it's a leaf, it doesn't work. Um,
I see. Okay,
so
I got it.
um, okay, returns 1. Now I need to add all the leaves.
Mm-hmm. Okay, now you are not at the base case anymore. You have treated the base case. To make it
Hmm.
easier for you, since it's a recursive function and they're pretty tricky at the start, take some examples. Okay, so let's say you are here. This is your tree: 11, 10 on the left, and 17 on the right. So
Hmm.
what you can see is this and what's on the left and what's on the right. That's it. Because unique paths first, it returns a result. So here you have left, and here you have right. So how can you use that to build the answer for the current node, this one, 11? And what you have is only 10 and 17. You cannot see what's deeper than that.
Hmm.
If your case is 20, what you have is 29 and 11. That's it. You don't know 10 and 17. So you have to construct your answer from an answer from a sub-problem or a
Hmm.
sub-answer. You see?
Yeah. So okay, I'm going to try with 20. Mm,
Mhm.
so int left and int right, and there's nothing here, so it would be again left. Okay, so left would be 1, right would be 1, and so then I would need to go back, and I have 1 and 1. Mm, I don't know how, where should I return the value?
Okay.
Should I
Yeah.
just
First, let me, tell me how are you going to solve it, and then we will figure out how to return the value.
okay?
But let's
Okay,
start
so
small, okay? So um, answer of 10. What I mean by this, a binary search tree of it has only 10.
mhm,
What is it?
okay, 1.
Unique unique of 17.
Yeah,
1,
also 1, and 11 would be 2.
11. And since it has on the right 10 and 17. That's going to be 2. Or I can do, you know this VST notation, right?
Yeah.
Okay, cool. And unique paths of 32.
1.
Yeah.
Of
29.
29 would be also 1.
Yes. 20.
3.
11. 29. Then 10, 17. Yeah. Okay. Now we have these examples. So iterate on some ideas of recursive relationships and test if they're correct.
Just return right plus left. Because if it's not a leaf, then we shouldn't, well, it doesn't add
Exactly.
anything to the sum. So just
Exactly.
return right plus left.
Exactly. And that's the answer.
And just below here.
Yeah.
Oh,
That's it. Okay, 14, not bad. Okay, did you feel that trying some examples didn't help you to come up with the recursive
mhm.
relationship? Okay, so try to do
Yeah.
that maybe more often because I saw that you didn't know where to start from. You were kind of stuck.
Mm-hmm.
Okay, so this is done. What else should we do?
Oh, there's, should we do lead code or, because there's one here.
Okay, okay. Yeah. Can you please upload it to GitHub? This
Mhm.
one?
Yeah, and wait, should we do the time and space?
Yeah. You will write that in the document.
Okay. So, but should I do it offline or do it now?
No, no, now, but right after putting the link, because let's just
Oh.
put one row,
Mhm.
fill one row of the document. We will fill the complexity, and offline, I want you to fill the other rows. You know,
Okay.
yeah, just to start with filling the rows of the document, to
Mhm.
make it a bit easier for you than to fill everything. Since now we have already the code, so
Mhm.
just upload it to GitHub. Do you have a repo?
Yeah. Yeah. Okay. Is that I wasn't sure if to do it.
I can show you how to do it quickly. It's
But should I do it directly on GitHub? Because
yeah.
I okay. Yeah.
Do you have any
Um,
other suggestion?
no, I was going to like copy it to a local and then push.
No, no. That's why
Mm,
I was saying that it's easy. Yeah, you have lead code questions, but it's private. Yeah, okay,
mm,
just create file. Can you expand it? Because
yeah.
okay,
Uh,
add file.
okay.
Yeah, name
So
the
this is going
file.
to be unique path. Oh.
Yes, just copy paste the code.
Mhm.
Yes, and
Okay.
at the bottom,
Okay. Mm,
uh,
right.
you can like hit commit. You don't have to write a message. Just commit new file, and that's it.
Okay, perfect.
You have the link, unique paths, .cpp, copy the link.
Here. Oh,
Yeah, yeah, just right click and copy the link. Yeah, from there.
do I put it or on the this document or on
Yeah,
the
that
chat?
one, that one. Go to the bottom
Oh, oh, yeah,
to the
yeah, 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 yeah.
table.
Okay, okay.
Yeah,
Hmm.
problem two, right there. Yes. Okay. Now answer
Okay,
the time
yeah, yeah.
complexity and memory complexity.
Okay. Um. So, okay, let's look at the code also. So, for the time complexity, well, we have to visit every node. Yeah, so it's just traversal. So it's uh, oven.
Yeah.
Mhm.
Exactly.
Okay, the memory complexity. I would say it's O of n, but you told me that um,
Not over.
n log n.
N log n or log n?
Yeah.
Why n log n?
Mm, I don't know.
Okay.
Um,
Where is the memory coming from? Let's track that down.
okay, so when we're these variables, like they only have a value here when we get to the leaf. So before the like we have like a stack of
Mm-hmm.
all the yeah all the paths before we get to the leaf. So
Yeah.
uh, yeah, I would say O of n because we like in memory we could have all the nodes except for the leaves because we haven't gotten there yet. So we haven't like released those spaces of memory. So I would say O of n.
No, it's not.
No.
Mm, no.
Mm. Mm. Okay, so wait, do I have the wait, where's that? Oh, here. Oh, wait. Okay, here. Oh, this is a different one. Okay, so if I start here, so I would be saving one, two. Wait, no, no. Wait, let's start in the 70. So left and right. So I'm saving one, two, and then these three, four. But then I get to the leaves and like the stack starts like releasing. So log of n.
Here it is log of n. And I think you're, okay, hold on. If you are at 61, let's say, what does your
Mhm.
stack value hold? What does it hold?
Nothing, because there's no left or right.
What?
Oh, one.
No,
No?
no. The stack
But if I'm,
always tracks what's behind it. Always tracks the function that called it.
oh, yeah, okay.
Otherwise, it's going to be lost.
Hmm.
So 70 launches 55. 55 launches 59. 59 launches 61. You will always have the path that we are discussing and counting. That's what the
Okay.
stack holds. That's what it always
Hmm.
does. So in
Okay,
a,
but that would be only for one, like the, yes, it would 70 calls 55, which calls 59, but 55 also calls 20, that calls 48. So, and
yes,
15 and 9 also calls 57. So
yeah, but
wouldn't it
over
be O
time,
of n?
no. At the same time, they're not going to be on the stack at the same time. You always have one node of the same level. You cannot have 55 and 97 at the same time. You cannot have 20, 59, 85 at the same time. You always have one.
But if I'm doing left and right, couldn't I?
Yes,
Wait, I'm going to.
yes, but what I'm saying is that at the same time, your stack only has one node from each level. Then
Okay.
it gets popped. Okay, look. What happens in over time? Let's start with chronological order. So 70 calls 55, 55 calls 20, 20 calls 84. And then when we finish calling 84, when we do left plus right, we return, it's popped from the stack. And we get back here. And 20 is treated, it's popped from the stack. We go here. Are you following me?
Yeah.
And so here we have only two at the stack, this one and this one. Then 55 calls 59. 59, we push to the stack. We push to the stack 57. 57 is treated. We go back to 59 and this is popped. And then we push 61. And at 61, you will have 61, 59, 55, 70. We can call your, oh, you have premium mode. We have access to this tag. We can do it on CLine.
Okay. Yeah. Okay. So I think I'm getting it, because it's not calling both functions at the same time. It's first doing one and then doing the other.
Yeah.
Okay.
So no need to run it here. No need to run it, I said.
Uh, do you need to? I don't know. Do you need to
If,
run
if
it?
you feel that you understand it, then
Oh, no. I think I got it.
okay.
Yeah. Yeah, because I was thinking like the like these and these were at the same time, but it
Mhm.
first pops. Okay.
Yeah,
Yeah, I think I got it.
okay. So the complexity is, well, the general idea. So if you have a balanced binary search tree, what is the height of the tree? So the height of the tree is the complexity, the memory complexity, because
Okay.
that's the number of maximum calls, recursive calls at the same time, which is going to be the same as the call stack. So if you have a tree, for example, that's one path, only one path, so that's an extreme case. It's like a tree. It is a tree, but not a tree at the same time. It's only one path. That's going to be O of n, as you said at the start. If you have a balanced example, then the height of the tree is going to be log of n, as you said the third time, I guess. And both of them are correct. And sometimes there's the other case where it's not balanced, where it can be not between log n and n. So that's the range. The lower end is log n, the upper end is n. And you can call the complexity just O of h. And you define h as the height of the tree. And describe, show the interviewer that you understand that the height of the tree can be log of n in best case scenario, or n in worst case scenario.
Yeah. Okay, I got it. So, okay, here it is. So the memory complexity is going to be O log n, because, well, it depends. Should I put log n?
No, for memory, put
N,
O of h, O of h. And,
yeah.
describe something about h, as define h as the height of the tree, and say what I said about the relationship with log n and n. Hello? Someone? Hello? Hello?
Dhia?
Hello, man. I'm sorry. I don't know what happened. I have no idea what happened.
What was it, you or was it me?
It looks like it was me. Yeah, it was me. I'm sorry. Really sorry about that.
Okay, yeah, no problem. So the maximum number of elements it can hold is the height of the tree, which can go from log. Okay, I think it's good, the memory complexity.
Yeah. And also it's called skew to the left or skew to the right when it's n. Hold on. Go to Visual Algo.
Oh yeah, it's here.
Okay. Create. You see skewed left and skewed right.
Oh,
This.
okay.
And this is skewed right.
Okay, so if it's like a straight line down, it would be n.
Yeah, exactly.
If the tree is Wait, heavily skewed. Sorry, English is not my first language.
No, no, no problem. You can say skewed to the right or left. That's it.
Ooh.
Okay. Do you have another question
Mm,
about something
no.
you had an issue with?
Well, maybe we could try dynamic programming. We like did a little bit last class,
What did you
but
do
maybe we did Fibonacci.
in the class?
Yeah, you don't remember?
Together or in the class? Do you call this class in our
Ah,
session?
sorry. Yeah, I call this class. I don't know. This is I don't know tutoring or something.
Yeah, yeah. Well, I'll just call it session,
Okay, yeah,
coding
we did it
session.
last
Yeah,
session.
I know, I remember. Yeah. Yeah, but still, I think for you,
Maybe too much.
no, no, not too much, but let's do more recursive functions.
Okay.
Look, DP,
Hmm.
once you're good with recursive functions, it's gonna look easy.
Okay.
Yeah. Um, the thing is that now, bless you, uh, what I'm seeing is that you're struggling a bit with finding the recursive relationship of the recursive function. And also, you always go for the global parameter, which is
Mhm.
normal. I mean, but over time, once you get used to making the function return the result itself and know how to write the base case and the recursive relationship, then you can say that you're good with the recursive functions. And once you're good with the recursive functions, DP is gonna look easy.
Okay.
Okay. Um, we can do another recursive problem. We have done this
Is that?
together.
Yeah, we did. Uh-huh. All the ones that said to do, we did.
Yeah.
Well, except that one. We did. We haven't done that one.
This one, did we do it? I think we did.
Mm-mm.
We
No.
did this one. It's
Yeah.
almost it's similar to this one. But you can do it offline. You don't need me. With this, you
Okay.
don't need me. Right? It takes a good and with this number of paths. Oh, did we do this? Path in a grid?
No. Mm-mm.
Really? Number of paths. We haven't done that?
Mm-mm. Wait. Maybe let's check the playgrounds, but I don't think.
Number of paths. Unique paths. This one. Oh, we haven't done it.
Should we do it, or is it like too easy?
I don't know. Maybe it's not gonna be looking easy for you.
We could do that one.
Yeah, let's try. Okay, how much time do you have? I don't have much. Okay, okay, we're good. Okay. Yeah, that problem is already here. That's sleepy. Um, okay, let's do this one.
Okay. Um, Wait, let's do another playground, a new playground.
Okay. Right.
Okay, so this is going to be long, longest palindromic ah, string. Okay,
So, palindromic
wait. Did I write?
substring. Yeah, this is substring. You know the difference between substring and subsequence?
Oh, substring is uh, like a string within a string, like a section of a string.
Yeah,
But
contiguous elements,
subsequence.
non-contiguous.
Oh, okay.
You can skip in subsequence, but in substring you don't skip. They're
Okay.
attached together.
Okay. So, should I start the timer?
Yeah.
Where's the timer? Here. Okay, so I'm reset. Okay, so it returns a string, longest. Wait, substring. Okay, so okay, so I should look at an example.
Yeah,
So
sure.
let's say, ah, mm, oh, so I don't know. I could do C, B, A, B, A, D, D. Okay. So doing C, B, A, B, A, D, D. So here the longest palindromic substring should be ABA. Mm, so I need to find a base case. Mm, but I don't know how long the palindrome is. So mm, and it's recursive.
Not necessarily for this one.
Oh, okay.
I know that I have wrote it under recursive functions, but you can solve it in any way you want.
Oh, okay, okay. Um, Wait, so I'm gonna try like a brute force, like anything. Mm,
Yeah, you can.
the longest palindromic substring. Oof. Okay, so first I need to see if a substring is a palindrome, and then make sure it's the longest. Mm, I mm, I'm thinking how could I compare different characters to see if it's a palindrome, but I wouldn't know which characters to compare because I don't know the length. So
Okay, first, you have three characters about your answer. The longest, palindromic, and substring.
mhm.
Okay? You are thinking brute force. So think when you think brute force, think of enumerating all the cases.
Okay,
What
yeah.
are
So
the
I would take
possible Mhm.
substrings
Yeah, how
and
many possible substrings do you have?
uh, it's the length factorial.
That's
Mm,
the ordering complexity.
Uh,
Arrangement complexity.
so the I don't know. It would be a lot.
No. Okay. Uh, the substring has start I and nj.
Mhm.
How many I and j can you have?
Well, wait, it's 1, 2, 3, 4, 5, 6, 7. So 6 and 6. So n minus 1 and n minus 1.
Yeah. So the possibilities.
Wait, really?
I j is
Um, so 36 or
what do you mean 36? This is the space. Do you agree with me?
wait.
Ij is in 0n times 0n. Do you understand this
Mm-hmm.
notation?
Mm-hmm. Yeah.
Yeah. So how many substrings can we have?
Yeah, so 36.
What do you mean 36? We have n, in function of n.
So 49.
I need something with n, not a constant.
Wait, I'm lost. I'm sorry.
With n, use n.
Uh-huh. And
N is the length of the string.
oh, and squared. And squared.
Yeah,
Okay.
yeah.
Yes.
Nice, nice,
Yes.
nice. Okay.
Okay, sorry. I
No, no, it's okay. So fine. Okay, so we have n squared possible substrings. Okay, from these substrings, can you check if each substring is palindromic or not?
yeah.
Uh, okay, and
Uh,
then can you take the longest?
yeah.
Okay.
Okay. Perfect. So I'm gonna start with um may, maybe set like separate all these substrings and then check if each one of them is no. Okay, no, I got it. Okay. So, four
Mm-hmm.
for to I.
Mm-hmm.
Yeah. Oh, wait. First I'm going to so string mm, palindromes. That's how you make an array of strings. I forgot.
Do a vector. That's not like you have
Oh
to add
yeah.
the brackets after palindromes, but the vector is easier.
Oh,
Mm-hmm.
okay. So
Nice. Okay, that's a good start.
so now I have the window the of the substring, but I need to check if it's a palindrome. So I would check the first to the last, and then the second to the second last, the third to the third last.
Um, do you know the substr function in string?
Nice. Yeah, so string current
Mm-hmm.
equal to s dot substring. So from I to j.
No. The first one is the starting element and then the length of the string.
Oh, okay. So it would be j minus I. Ooh.
Then
Ah.
j
No, no,
minus
no.
I plus 1
Stop. Wait. Siri. Okay. It would be j minus I.
plus 1.
Oh, wait, j minus I plus 1. Oh,
If I is 0, j is 1. Then the length is 2. 1
okay.
minus 0 plus 1.
Yeah. Okay. Um.
Mm-hmm.
So now I need to have another for loop to check the if it's a palindrome.
Yeah. Okay. Can you write the recursive function for that?
Hmm. Okay.
Can you do it here?
So. Mhm. Uh. Okay.
Okay.
Um.
Now I want you to skip it. Do do later. Skip it, use it,
Mhm.
skip it, and then get back to it later.
Okay. So is okay. So if is palindrome cur uh palindrome that push back cur.
Do you need to save them?
Oh no, I don't. No, I don't. Uh no, this is not okay. So you just need string
Mm-hmm.
longest palindrome. All right. Ooh, if wait and cur the length equal is greater than uh longest palindrome the length. Oh,
Length is a function, by the way.
Sorry?
Length
Oh, yeah.
is a function.
Longest that palindrome equal to curve. So return longest. Okay, so I think I'm good to go. Yeah.
Okay, now we can do the palindrome.
Okay, so okay, so it's recursive. So what would be the base case?
Do you have another idea other than the recursive implementation?
Well, yeah, yeah. I just a for loop, you know, with the so it would go from 0 to length divided by 2, and then it would check from I to length minus I, and check those two and see if they are
Yes.
but I don't know how to make that recursive. Oh, okay. The base case would be that those two letters are, well, you would compare those two letters, and if those two letters are the same, then it would go to the next two letters.
A base case doesn't go to the next.
Okay, yeah, no. So the base case would be if it's in the middle of the word.
Yeah.
Okay. Okay. So if oh, how, like, if the index is like s dot length divided by 2, but like
You
what
need I and
variable am I?
J. Well, you either need I and J and S, or you measure front and back. Do you know the functions front and back?
No, but I
Front and back in front gives you the first element and back gives you the last element.
okay.
So you know you can get the first element from the top and from the back.
Mm-hmm.
Yeah.
And then if okay, I think I have something. So we check front and back, and then we make a recursive call with a substring without those two letters.
Exactly.
Okay. So wait, but if it has an odd number, if it has an odd number, oh yes, it can be a palindrome. Well, but it doesn't matter if it's odd because the middle doesn't matter. Okay. So if s dot length is less than 3, less than or equal to 3.
3.
Yeah,
Do you want to
because
do? Is this for a base case?
I was thinking, yeah.
For base case, it's length 2, right? It's either you
Sorry?
have one character or two characters. For base case.
Yeah. 2. Yeah. Because if it's 3, then you would take, yeah.
Exactly.
Okay.
Length is a function.
Oh yeah. Okay. Okay. So if should I do two separate if statements? If there are two letters, if there are two letters, compare the two letters, and if it's wait, what I'm thinking is this. So if as that length is equal to 1, return true. Is equal to 2, 0 is equal to.
Okay, now I want you to use front and back.
Oh yeah.
Dot front, dot back. You can,
Is it a function?
yeah, function. Or you can do this. Return.
Oh yeah. Mm-hmm.
Right?
Yeah, you're right.
S
Mm-hmm.
dot front equal to S dot back.
Oh. Oh.
Okay,
Mm-hmm.
nice.
Okay. So now mm, wait, so what what I was thinking was the to cut off the front and back, but I only do that if if the front and back are the same. So I need another if statement. So if uh, if s dot front is different from s dot back, return false, and then if they're the same, make a recursive call with.
Yes.
Okay. Okay. So base cases, and then recursive calls. So if s dot front is different from s dot back. Oh yeah. Oh, I make so no. Wait, it was correct because I only wanted to return if it's false. Return false, and then else is palindrome with s dot substring, which starts at 1 and has a length of s dot length minus 2. And I think we're good.
Return.
Hmm?
Return line 14. 14.
Nothing.
You don't return, you have a boolean.
Yeah, but in the base case, don't I?
What? No,
Yes,
you need a return.
but I only return if the whole string is a palindrome.
You always return. That's the base case. But even if you're not in the base case, you need to return. Otherwise, we'll get a runtime error. Not runtime, compilation error. That this doesn't compile.
Wait, I'm sorry.
You have to return. Add return. Here. Return this.
But why do I need to return? I'm if I'm making a recursive call to a function.
Yeah, but what is the return of this one? That's another function. It's true that it's the recursive one, but you need to return. It doesn't work. Otherwise, it's really doesn't work. Okay,
Okay.
let's test.
No, sorry.
Actually, we don't need this. We need this. I will tell you why. Okay, and
BB.
okay, let's remove this.
Oh, mate, that's what happened with me in the problem I sent you.
Yeah, I told
Ah,
you. I told you you don't have a return.
but I thought that it was because this one wasn't the base case. I didn't need to have a return. Okay,
No,
sorry.
you always return.
Okay. Is that I when I think return, I think it like exits the function and doesn't do anymore. So it's okay.
No,
Yeah. So
they
always
are
return.
recursive calls. When return calls this one is called is calculated and then returned, and then the return goes from function to function to function until
Mhm.
it goes to the very first function that launched the call.
Okay. Hmm. Ooh. Okay, but this is like n cubed.
Yeah, so I want you to, as usual, just put the code on GitHub and answer the questions.
Okay.
And you did it in pretty. The time is not bad at all. 26 minutes.
Well, but like the time complexity is terrible.
Yeah. So what is the time and what's the memory capacity?
Okay. So first I'm going to put this code on GitHub, which is here. It's ah, wait. Add file, create new file. Longest. Okay. Mm, let's go here. Okay, longest palindromic substring. Here is the answer. Okay, so time complexity. No. So, okay, so I have these two for loops, which are O of n squared. So it's at least n squared, and then I need to take these into account, which, yeah, it's O of n.
Oven,
Well, it's huh?
oven, memory,
Well,
time complexity.
yeah, time. Well, it's n divided by two, but
The whole thing. Are you?
no. It's n cubed.
Yes, it is n cube.
Oh, okay.
Why is it n cube?
Well, because it's n squared from these two for loops, and then is palindrome is n over two, which is n.
Mhm.
Mm, six. Okay.
What is that, man? Okay. The first two loops. For what are they?
Oh, okay.
For what? The first two loops.
Uh,
No,
to
don't remove. Don't remove. What you're typing is good. It's correct. I'm just asking a question. What are
oh
the
yeah,
first two loops for?
for the substring to generate all the substrings.
Exactly. Yeah.
Okay.
So can you type that down so that you always like, keep it in mind because you first thought it was n factorial.
Mm-hmm. Wait. Okay. Because I used two for loops to generate all, which make it n squared, and the function is palindrome is mhm. Okay. And the memory complexity. Well, okay, so I'm doing nothing here. Here I'm making. Okay, so until here, until is palindrome, it's constant, right?
Um, if you ignore longest palindrome, then yeah,
If I ignore what?
longest palindrome, that's a string.
Oh, okay. So so I need to save longest palindrome, which can be up to s, and then
So can you give me the memory complexity of the recursive function?
mhm, yeah. So mm, the memory complexity is, I'm going to say n, because I it's doing so the entire substring, then a substring, and before we get to this point, it's saving the whole stack.
So
So
yeah, how much is the complexity?
I would say n.
Yeah.
Okay, so it's n plus s.
Well, what do you mean by S? What's S?
The size of the entire string.
It's N, right? Look, we call it N.
Oh yeah, but that would be the complexity of this function. But of the entire main function, wouldn't it be, because I also need to save the longest palindrome, which in the worst case is s, or does that not matter?
It's
Okay,
N. So then,
okay. Mm, which, okay. Wait, no, I think I messed up on that final part. Oh, yes. Hmm.
uh, it's oven because of the stack. You know that it's because of the stack, right? It's
Hmm.
over N over 2, to be precise.
Uh-huh. Yeah, yeah,
Oh,
because
dude, we forgot about the length of the string.
what do you mean?
The length of the string, we forgot about it. It's N over 2. We are not caching I and J. We are caching S, so it's being stacked in the queue, in the stack, sorry.
Yeah, all the states of the substring. So
Yeah,
for example,
so
here it would
it's
save
in,
ABBACCC, and then it would save BBACC, and then it would save BAC, and then A.
yeah, that's gonna be all saved in the stack.
So it would be like, yeah, it would be not exactly. Oh, wait. So it would be, oh, n
We,
squared.
yeah,
Ah, really? Oh, this. Ah, yeah, so we're not saving the indices, we're saving the entire
yeah,
string. Yeah.
but you can make it N if you only use I and J,
Mm-hmm. Okay.
or like two pointers method. And you can
Great.
use an iterative solution. You know how to write the iterative solution for palindrome?
Sorry?
For palindrome, iterative solution, not recursive.
Well, like I was asked this question in an interview, but like a low, not, it wasn't like, it was for the like first year internship, like not a
Oh,
SWE internship, but
yeah.
like Google, like engineering practicum and things like that.
Okay.
And the question was literally, tell me if a string is a palindrome. And what I did was, like I said, a for loop that went from 0 to length divided by 2, and compare um, I with length minus I.
Mm, minus one minus I. Yeah.
Uh-huh. And Yeah, I didn't get the internship, but
You answered the question.
yeah.
Okay. Uh, okay, I think this is good. I mean, Christopher, we better stop here. Uh, okay. Do you have any note or something to tell me or ask?
Um, no, I think notes would just be that I try to work a lot of stuff in my head, and I need to look at examples and try to, you know, follow my logic through an actual example instead of like trying to figure it out in my head.
Yeah.
And I need to just make more time to practice. Is that
Yeah.
I haven't been practicing, so yeah, I I I think like I'm happy, but I definitely just need to set aside more time to practice.
Exactly. Um, as I said before, you're really smart and you understand pretty fast, but you have to practice. Without practice, uh, you
Mhm.
know,
No, I totally get it.
you
Mhm.
get my point. Because it's about practice. But your advantage is that you can get the results of, let's say, someone who's average. He has to spend 100 hours. For you, you only have to spend 50 hours, and you will have the same understanding of
Mhm.
them. You see, that's the advantage that you have over other people. But if you do not practice, then people people are going to be moving forward when they practice, even if they move slow. But
Mhm.
even if the smartest person without practice, he's just gonna say there. He's not gonna be able to make progress. You see,
Mhm.
and try to
Okay,
make it a habit.
so
Try to make,
uh-huh.
you know, solving. Try to solve a problem each day. Even if it's easy, it's fine. But try to make it each day. That's why I insist on having a GitHub repository so that you get addicted to seeing that green
Yeah, that green
box.
square. Uh-huh.
Yeah, yeah.
Uh, so should we set aside some problems right now that I could do during the week?
You have these problems, the recursive ones. If you could do them, then it's going to be amazing, like really amazing.
Okay.
If you want to do some other problems on LeetCode, of course you can. If you're stuck, let me know. Of course, I'll be answering if as soon as I see your messages. And yeah, I
Mhm.
mean, as I said, what you already have, it depends on the rhythm that you will be following to
Mhm.
work.
Mhm.
But you have to, increase the speed to be able to solve all these problems that I have.
Yeah,
It
totally.
might even take you 2 months if you go with this rhythm. If you increase the speed, maybe a month or a month and a half, something like that. So try to, solve more problems. And as I said, I'll be always here. Just ask any
Mhm.
question you have. I'll be happy to
Okay.
help. Um, yeah, if you could finish this in a month, then it would be great.
Okay.
Even 1 month and a half is not bad because there are a lot of topics. There are really a lot of topics, and I was
Okay.
working with this guy who was pretty much full time on it, and
Yeah.
we did them in around 2 months, something like that.
Oh.
But he was
Mhm.
full time. And he was
Mhm.
like such a hard worker. He was working so hard and always
Yeah.
writing comments and asking me to see and to correct and stuff like that.
Yeah. Okay. I'll work on that.
Yeah,
Definitely.
but consistency matters more than working a lot. Just try to be consistent. Have a
Mhm.
steady momentum. Okay, just steady momentum. Try to study at least an hour a day. An hour.
Mhm.
If you could solve a problem, then good. Otherwise, you can leave it for tomorrow. But try to always block an hour for problem solving.
Mhm.
And over time, it
Yeah.
will add up. It will add up. And that's how you will, how you will understand a lot of things and how you will make progress with solving problems.
Mhm.
Okay.
Okay.
Yeah. So by the way, my calendar, a lot of people have access to my calendar because I I have I have many students. Well, I mean
Mhm.
around five, something like that, and I also do consulting. So
Mhm.
if you don't book early, then it might be taken. I don't know. That's why I
Mhm.
ask you
Okay.
sometimes because you tell me that you want to have the same time. So
Mhm.
if you are sure about this, then book ASAP. Otherwise, it's going to be taken. And today, for example, if this was taken, it I would have you would have to do. Oh no, I wouldn't be available because
Mhm.
like I now have a session, and then I have stuff to do, and later at night I'm gonna have a session. Anyway, it's gonna be a busy day. So
Mhm. Yeah, I'll make sure to schedule it right away.
yeah, yeah. As soon as you know, of course, because you also have your own stuff to do, and sometimes you don't know
Mhm.
if you will be able to make it a week like the next week or not.
Mhm.
Yeah. Anyway, keep practicing. Try to practice more. Um, and look, be consistent. Practice more, and over time you will improve. Trust me. I'm sure that you already see that you're improving. You're improving, but
Mhm.
I know it's slow. It looks slow, but it's not slow. If we can do that, we can do this next session because I have to go in a few minutes. But we can look at all the things that we have done together, and you will see how many things have you learned. You see,
Yeah.
just try to be consistent, and
Mhm.
things are gonna stack up and add up, and you will be learning a lot of things. Okay,
Okay.
so
Yeah. Definitely.
I'm done. So don't forget. Yeah, let's do the payment for this week.
Mhm. And
Remove
last week as well.
15 minutes. So how's it gonna be? It's gonna be 150.
Should be okay. I'll make sure. Yeah, I'm gonna do it right away.
Yeah. Thank you so much, Samuel.
Okay.
See you and talk to you.
So
And
yeah.
yeah,
Hmm.
cool. All
Okay.
right. Bye, man.
Bye, Dia. Thanks.
Sure, Samuel. Bye.